afternoon to the next session of embedded software testing. This is a Unit 4 series of lecture series. Today is lecture 2. We will study and discuss more on embedded software testing, software integration, and we will try to see the test strategy and its benefits and comparison of different strategies, then top down, bottom up advantages, disadvantages, integration testing, other types also we'll discuss. And before that, I just would like to have a recap and add some more points to what we had discussed in the last session. That was on integration. We know that 3 levels of testing we can do: component, integration, and system. So basically, we do individual components, and those are under test when we do the unit testing. Next one is the integration testing, where we combine logically different components based on the complexity or the feature wise or the functionality of those components. Then we will interact with the other similar logical or interactive groups to make sure that those are getting integrated and the behavior is verified. The last type will be the system testing, where as a black box everything will be tested. So basically what we do, we define the test objective for integration test, which what qualifies the system we want to verify. Then devise the test cases, program the test, execute the test, and analyze the results. So those are the steps we will follow for testing. Then we had gone through integration testing definition. It's a process of aggregating different components to create larger components, so that larger components can be tested together with similar larger components. Integration testing done to show that even though components were individually satisfactory, the combination is incorrect and inconsistent. The combination is very important. It's not just enough to test at a component or individual level. So we also had gone through definition of what is integration. So basically, it's not enough to have unit testing alone uh, to get a stable or functional correct system. So many defects are related to the integration of modules. If the requirements are not formally described, everyone has to make their own interpretation of those requirements basically. So this is not a problem as long as these interpretations are not related to interactions with other modules. But incorrect interaction between modules is often caused by these interpretations. This is the problem actually. So what is the best instrument to detect that is with the help of integration test. So basically, integration strategy is a decision about how different modules are integrated into a complete system. The integration covers both hardware and software, as I said. In terms of hardware, it's called as a hardware software integration, and it's called as software integration. It is basically the different software modules and their interactions will be verified. And system integration, system hardware integration, system software integration, the other terms of embedded system integration they define. The task of creating a properly functioning system from its constituent components. The components could be hardware, firmware, software. Whereas in system hardware integration, are the components wired together correctly? That means especially the hardware components are tied properly within the system, and those components are tested against their behavior. And the last part is system software integration, where typically it assumes hardware integration is largely done. There are no issues with the hardware, but before we deliver or accept the product, software modules will be verified with the hardware, how it is behaving and all that. That's what we do with the system software integration. So Integration steps, basically we need to create list of all software components, identify the grouping and dependencies between each of them, list out the strategy to perform these categories of integration. The list could be based on the uh, aspects like functionality, performance, subsystem integration or interaction, databases, the kind of database that we use, and what interface, especially from the signal perspective, how it is derived, then the control of the various program elements, then safety and security aspects, and conformity. Okay. So basically the goals of software integration is to expose faults in the interfaces and in the interaction between integrated components, to find collaboration and interoperability problems and isolate the causes, to reveal interface and cooperation problems as well as conflicts between integrated parts. So the faults could be in terms of interface, such as the formats of the memory or the file which is not compatible, whereas it is working individually, but when you interface with the external memory or any file handling, there could be an issue. Similarly, the data exchanges are not properly there. Typecasting is an issue when it interacts with the subsystems. All these sort of a interface issues and coordination or cooperation problems within the modules will be revealed. And we have types of integration as big bang integration, bottom up integration, top down integration. I mean, this is how the approach to the integration is being done. Sometimes component integration test is also called as an integration test. Uh, that is considering the small system integration test. So system integration test is also called integration test in the large system where the external systems are more involved. So it depends on the complexity of the system. So in Big Bang, it's a simple testing type. All modules are integrated and the system is tested as a whole, basically. So completely the system, not the end system, but the system which is enough to test it. That way it is going to be banged from the uh, testability perspective. The main advantage is that no stubs or drivers, as we have seen, are required for this. So with this strategy, it is but the problem is too difficult. Uh, it is difficult to find the causes or defects, and the integration can only start if all the models are available. And it's not like a stepwise sort of a thing. So basically, it's a coupling with the entire system. Similarly, we have seen after all components are unit testing done, we may test the entire system with all its components. Disadvantage. The next type of integration testing is the bottom up integration testing. This strategy is useful for many of the systems. It starts with low level modules with the least number of dependencies. I mean, basically it uses the drivers, test drivers it is called. The integration can start very early in the development process. That means we don't have to wait for all the modules to be completed. And then when the modules are done, we can write the test drivers and start the integration test for the completed one. And incrementally we can close all the modules. Basically, advantage is that it will lead to an early detection of interface problems, and these problems can be isolated very easily. Disadvantage is that we may have to deal with many test drivers, and we have to use it for carrying out different strategy, and it's a tedious one. And we also had gone through a bottom-up integration testing example where higher level module A and lower level module B and C are there. So basically, we develop a test drivers for B and C. So we test B and C individually, then we test A such that it calls B. So if any error, we know that there is a problem is in A or in the interface between A and B. Similarly, we test A and we develop the driver such that it calls the C. And if there is an error has to be in A, or the error could be between A and C. Okay, the next type of integration testing is top-down integration testing. In this strategy, the control structure of the system takes the lead. Basically, the control structure is developed in a top-down sequence, and this offers the ability to integrate the modules top-down, starting with the high-level control module. At every new level, the connected modules at the corresponding level are integrated and tested. As we go down, the connected modules will be tested one by one. The role of the there could be some non-existing modules also. Those can be replaced with the stubs. Here we use a term called stub. And drivers we use it at bottom up, and test stubs we use it top down. So advantage is that the look and feel of the entire system can be achieved. That means user has an idea of what are the top level modules, how it is architected, and how it is getting flow down into individual modules. That is the advantage of taking up top down integration. Disadvantage is that impact on low level modules may lead to changes in top level modules. So we don't know what is the impact, and we may have to wait for all the modules to be completed. We cannot do a progressive thing until otherwise the top level module is done, so that if any one or two low level modules are not done, we can stop it and test it. So we need a number of stubs for every integration step. So we also had gone through an example of top down integration, where A, B, C, three modules, A at higher level, B and C are low level. So A we will test it individually with the help of stubs for B and C. Test A such that it calls B, stub for C, and if there is an error, we know that there is a problem in the B or in the interface between A and B. Similarly, while we are testing C, we stub B, so that altogether we focus on C, and if there is a problem, the problem has to be in C or interface between A and C. So the advantages and disadvantages of integration testing top down and bottom up are we will detail out in today's session. We also know that test drivers are not needed, or only simple ones are required. That's the advantage, because the higher level components that have been tested serve as main part of the test environment. So we don't have to have a test drivers. We already have a top level module. Disadvantage is that low level components not yet integrated must be replaced by stubs, because we are not done it, or it's not integrated, or it's not ready. So this can be expensive because we need to develop the stub. Bottom up advantage is that no stubs are required, but disadvantage is that high level components must be simulated by test drivers. So user will not have any idea about how the top level modules look like and how we can approach the integration testing. That is a disadvantage. And also the importance of why we need to plan the integration. So basically, successful integration will be enabled with the critical factors such as objectives, responsibilities, and resource planning, so that we know at what stage what are the type of integration we are going to do, and how the cohesiveness is going to be achieved. So basically, the product lifecycle or the project lifecycle outcome is purely based on the integration. So some the customer asks track or progress of development, he will similarly ask the progress of integration. The first question he will ask is, are you able to integrate and test it, the models that we have developed? How is it going on? How is what is the performance of integration testing? Whether you are able to integrate all the components, whether you are able to interact with the hardware or the actual system. How is hardware software integration going on? How is software modules interactions behavior is going or progressing? So all these sort of things is an outcome of the integration testing. So definitely there is a need of plan for the same, because it has a lot of stakeholders including resources, time, personnel, which are going to be identified for planning that integration. Similarly, integration considerations that we need to have is that we need to have an understanding of architecture, system decomposition. The architecture considerations could be open or closed architecture, or integrated or modular architecture, likewise depending on the type of system that we are trying to do. Definitely there is an architecture or high level design that needs to be considered for integration, and also we need to have an understanding on the interfaces, how the interfaces are associated, what are the types of unlocks or discretes that are getting involved. All these will be part of the interfaces, the signals. The next one is the hardware considerations in terms of hardware limitations or feasibility, or it could be anything. So we need to have a idea of the hardware, how it is built, because without the hardware we cannot be able to test many of the software modules because it's tightly coupled with the hardware. The last one being the software consideration. We know that the software modules have to be very cohesive so that they can be tested appropriately on the hardware. Some examples I'll try to provide interfaces so that you are clear about what sort of a used. The interfaces could be memory, port such as RS-232 or CAN or SKY, etc. SPY also is another example. Next we have a timer. Next you have a power interface. It's also very important, where some of the power up requirements have to be catered, such as within so and so time the booting procedure has to be completed and system should be up within certain time. So there we'll look into some of the glitches or any interrupts based on the power that also need to be considered for interfaces. Of course, we have analog interfaces, discrete interfaces. Discrete could be any switches, signals, LEDs. All these will be discrete interface. Then motor interfaces, it could be brushless motor, stepper motor, whatever it is. Again, this depends on what sort of a drive we have. It could be through any of the port, or it could be a parallel bus, or it could be an analog interface. But basically, the end target is the motor. So how we are going to interface with it actually? So it's very important for us to understand if the system is a motor based closed loop control system. Definitely, we need to have a feedback mechanism understanding by the system tester. Of course, we have DC, AC motor interfaces. These are types of interface. Let's not list out. Okay, so hardware related interfaces, we know that the hardware input output need to be cohesively used in the system integration test. So that is also very important. Software interfaces in terms of like any algorithms, uh, checksums, computations, all this will be multiple. All these things will have a multiple components involved. So definitely we need to consider the software aspects of the integration. So that is very important. Okay, so the last part which we had studied the last session is that integration test strategy. Ad hoc strategy is to integrate the components in order in which they are ready. So that is not a good idea basically, but you can do it. You can afford to do it in the beginning of the program. As a component has passed the component test, check if it fits with another already tested component, and or if it fits into partially integrated subsystem. We need to see whether that component, when it is ready, where it can fit, whether it can be tested. First we need to identify the components, its associated integrated subsystem or associated component where it is going to fit. Then accordingly the associated one also need to be addressed to make sure that both are integrated properly. So we need to write stubs to help the integration. Stub is a skeletal or special purpose implementation of the software component used to develop or test component that calls or is otherwise depend on it actually. It replaces a called components. That's why it's sub use. The other form of stub where we have seen in top down is drivers, where the high level components are going to drive the low level things. Sorry, in the bottom up strategy. Okay, so that was about the previous session. Now we will go through the integration test strategy in detail. We know that stubs and drivers are needed for integration test. So it is nothing wrong in having both actually. It is again subjective where we have to take a call. It depends on the complexity of the embedded software system elements. We can have both bottom up as well as top down approach. So it is again dependent. For larger systems where we have millions of code, definitely we need to divide the entire system into several subsystems. Those each several subsystems can be addressed in different strategies in terms of integration, but all that have to be planned appropriately. Either it could be bottom up or it could be top down, or some subsystems we don't need to have an integration at a top down or bottom up. We can go for the big bang integration testing where the entire model, entire group of modules can be tested all together. So that strategy also we can adopt. That is again subjective. Okay, so we have gone through the various types of integration test strategies. So we will try to compare these based on the book Mayer's 1979. So the table basically lists out different types of integration strategy. We will not focus on sandwich and modified sandwich type of embedded integration testing. So these are another type, but they are rarely used or it is not required to be understood at this point. Okay, so you can see the features that are listed on the left side of the table, and on the right hand side we have different types of integration strategies: bottom up, top down, modified top down, big bang. So basically it identifies integration when it should be done. So bottom up early, top down early, modified top down early, big bang at a later stage, because all modules have to be completed. Time to basic working program: very late, bottom up, early, late. So here to have it a matured working program. So bottom up will be at a later stage, whereas in top down early stage we can identify the understanding of the working system. Component drivers needed. Yes, for top down we need. Sorry, for bottom up we need, not for the uh, top down. Modified top down also can have test drivers or component drivers is also called. Big Bang definitely requires drivers. Stubs needed. We know that it's needed only for the top down approach, not the bottom up. So work parallelism in beginning. Uh, the ratio is something like medium bottom up, top down it is low, modified top down is medium, and at Big Bang it is very high. So that means parallelism need to be worked out. Ability to test particular paths. What is the difficulty? So bottom up it is easier, and in top down it is very hard, and modified top down it is easy, and Big Bang it is easy. Ability to path, plan and control sequences is easier in bottom up because we have the control on the smallest of the components in the entire system, and it's very difficult for top down. We don't know the exact sequence until we go through each of them. Big Bang it is easier. So these are some of the metrics that they have compared for integration strategies. Modified top down is something like a mix of both top down and Big Bang. So they adopt in some of the medium size, mid size complex integrated embedded systems. That is where they use it. Okay. So that is about strategies of different integration types. Now we will try to go through top down advantages and disadvantages. This is basically from a book called Stuart Anderson's material got from the web, which basically lists out the advantages and disadvantages, such as in top down if major defects are more likely at the top level module, top down is beneficial. That means we have more issues in the top level, then this is going to be advantageous. Getting input output functions in early can is test rating. That means as long as we have developed the more input output functions in the earlier stages, the top down approach will be beneficial. It leaves out the integration strategy of top down testing. So early demonstration of the main functionality can be helpful in highlighting requirements issues and in boosting the morale. That means as I said, you have more clarity and idea of what the system is behaving, and your understanding will be better as you progress on the integration testing of this type top down approach, because you start with the main functionality or the top level modules. Now let us look into the disadvantages of top down. It's too much effort for stubs. You know that top down requires stubs because low level modules are not ready or not enough to test. Then we may have to live with the test stubs for the low level modules. And also another problem is while developing the stub, if it is more complex, it can inject some additional issues or introduce errors. That's a disadvantage. Defining stubs can be difficult if some code is yet to be written. So we are unclear about what exactly is going to be implemented, but we are having the knowledge of that functionality. Based on that, we are going to develop the stub, but sometimes it is difficult to develop a stub where the code is yet to be written. It may be impossible accurately to reproduce test conditions. If there are failures, suppose we started top-down testing, and we found out that there is a issue with the system. It's very difficult to figure out or isolate where the test issue is there and how to reproduce it. So some of the issues like intermittent issues are very difficult. So that's the disadvantage with top-down testing. Some observations may be impossible to make. So we cannot observe some of the minor elements of the top-down testing modules. Encourages the idea that test and development can overlap. That means top-down testing have a close relationship with the development aspects. So basically, it encourages the idea that test and development can overlap. Encourages differing full testing of modules because low-level modules are not complete. So we are living only with the high-level modules, and basically we may not be completing the entire integration testing because it is partially done or partially passing. Some of them low-level modules are yet to be explored. Such things are difficult with the top-down integration testing. The next one being the bottom-up testing. I will correct the PPT. Okay. So what we do here is we know that test drivers are needed for the bottom-up testing, and advantages are such that helpful if errors are likely deep down in the dependency structure. So if the system implementer they think that it's more complex at the deeper level, especially on the device drivers or the hardware interfaces specific code, then it is better to take up this activity. It's going to be advantageous. The bottom-up integration testing. Test conditions are easier to create basically because lowest of the modules we need to understand and create the test conditions. Observation of test results is reasonably easy. There is a reduced effort in creating stub modules. We don't have to spend too much on the creating the stubs. Disadvantage is that we need to create driver modules, but arguably this is easier than creating stub code, and tools like some GUnit is what he has referred. So let's not bother about that. But basically, driver modules we need to create. So we need to have an understanding of that. That's a disadvantage. So, but it's easier than creating the stub because we can see the code and we can drive the values what we need to develop the driver. The entire system is subjected to the smallest amount of test. That means we are focusing only on the smallest part of the entire system because the top modules are included in the tests at the final stage. We are not addressing at the higher level. Incrementally, we are testing one by one from the bottommost low level modules, and as we go into the higher level, we are going to test at the higher level tests. Okay, so those are the advantages and disadvantages of bottom up and top down integration testing and the test strategy. Now there are other methods of integration testing also. We'll just try to touch base. What are those? Okay, the first one being these are all basically referred from the sources, how they have followed in the industry in terms of defining them or creating, because every industry is typically different than in general. Actually, they will adopt based on their need and complexity and the skills and the compactness. tools. So many aspects are there. All this need to be considered, as I said in earlier slides. Based on that, they will decide and they'll define a name for that type of a integration testing strategy. Okay. Next type of integration testing is hybrid testing. It is also called as a combination uh, type, combination integration testing. So it is clear that judicious combination of stubs and drivers can be used to integrate in a middle-out approach. As I said, it may not be purely possible to use stubs only with the entire integration, or it may not be feasible to use drivers alone for the entire integration aspect. Sometimes we may have to mix up both based on the complexity and uh, the type of the kind of ML system that we are trying to test it. So we need to do a judicial approach of combination of this. So we need to take care of this based on the type of system that we use. So that is called hybrid test strategy, which uses both. Also, for some groups of modules, we may want to take a non-iterative approach and just consider testing them all at once. This means we choose a bigger granularity for our integration steps. That means, some of the groups of the modules we may not be able to take up the iterative like bottom up, and we can take separately as a one shot testing when we are doing the other dependent modules. Those kind of things also can be done depending on the type of modules that we have. So this comes under the hybrid test strategy. So using this approach, there are range of potential criteria for deciding how to group those modules. So basically, hybrid test strategy deals with groups. As I said, grouping is a very important aspect in integration testing. Here, grouping is based on the features, functionality, requirements, performance, etc. So there are different criteria that we need to follow for grouping the various modules. So what are those? One is the criticality. Decide on groups of modules that provide the most critical functionality and choose to integrate those first. That means we identify critical groups which are very important to test, which are very important part of the entire embedded system. First you address that, first you group it, then rest of them will fall. That is one of the deciding factor. Then the cost. This is also equally important. Look for collections of modules with few dependencies on code lower in the dependency graph and choose to integrate there first. The goal here is to reduce the cost of creating stub code. That means uh, sometimes what will happen is we cannot be doing stubs all the time because it is going to add a cost. So we need to take a judicial decision based on how much cost for the development of stubs have. So if it is going to be too much, then we need to collect such modules which can have many less dependencies on lower part of the code, so that the stub we don't have to have much, so that the cost is appropriately taken care. So these two are very important. Here cost means not the rupee or dollars. It is basically the effort. Of course, at the end of the day, all it matters is the money. But we look for the efforts, how much effort is going to take, and complexity or criticality. These are some of the important deciding factors for identifying the test strategy. But bottom up and top down, they have their own advantages and disadvantages. Where you have a system having complexity, it's my suggestion, such as closed loop and more interfaces and large systems. I would say moderate to large. These kind of systems I suggest to have hybrid test strategy, where it mixes up both test stubs and drivers. Here, test stubs and drivers means top down as well as bottom up. So both being followed. Coverage and all are the second aspects. Once we have that integration done with a satisfactory test coverage and test reports for each of the modules, automatically the coverage part will be taken care. And wherever the gaps are there, then we can fit into any of the test strategies such as unit testing, system testing, all can be taken care. So basically, we need to address the entire system from this aspect. So that is where a hybrid test strategy comes into picture. But before hybrid, we need to understand what is bottom up and top down, so that we have an appropriate mix of test drivers and stubs. So that is where it's important. So there are other types of integration. We look centralized integration. This type of integration is used when a central part of the system is necessary for the rest of the system to function. That means without the central part, nothing works. That is heart of the system. For example, a OS or a kernel. So definitely we need to first address the kernel or the operating system first. That is centralized, and surrounding this centralized part, there are subsystems which can be tested subsequently. The central part is necessary to run tests, and it is too difficult to substitute this part with a stub, right? So we cannot replace a OS with another stub. OS has to be there for OS only for testing. So that is the central part of the fulcrum of the entire embedded software system. The architecture of the system is such that the central part of the system is developed first and made ready for production. That means this kind of systems, what they do is first they develop the kernel or the scheduler or the OS, and surrounding that they will incrementally develop subsystems one by one. So that's how the architecture will be laid out first. So after that, the new modules or the subsystems are used to upgrade the system or to add completely the updated functionality or the new functionality. So that is how centralized integration is going to be done. But here also again, centralized systems will have subsystems. Those subsystems we can adopt either top down or bottom up or hybrid, whatever it is. It depends on how large the system is or how complex the system is. So it's very important. So there are other types of integration testing. Just we'll discuss one or two lines for this. Layer integration. This strategy is used for systems with a layered architecture where we have application and libraries, mid layer, lower level layers like this, where the systems are there. So this type of integration testing they use it. So in this interfacing only happens between the layer directly underneath the below and the above. So we won't talk about the complete bottom up or top down sort of a thing. But each layer is tested in isolation using the top down or bottom up or big bang strategy. The next step is the integration of the layer according to a top down or bottom up order. The advantages and disadvantages are the same as top down and bottom up strategy. The integration and isolation of interfaces is much easier, and therefore discovery of the causes of defects is also easier because we have addressed the layers. So based on the layers, different other layers are going to be integrated and tested. Next type is the client server integration. This strategy is used for client server architecture, where we know that database in the server and the client will have UIs and all that sort of a embedded architecture where we have this strategy will be more appropriate. The client is integrated either top down, bottom up or big bang, and the server is substituted by a stub and driver. We can use the stub and drivers to replace the server. For the server, the same approach is chosen for testing server itself, like top down, bottom up, and the stubs and drivers are developed for the client. Finally, the server and the clients are integrated. Collaboration integration. So basically, a collaboration is a collection of objects which work together to achieve a common purpose. For instance, realization of a use case. We'll study what is use case and test cases derived out of use cases in the later stages. The system supports many collaborations because it has to realize many use cases. Many objects belong to more than one collaboration because we have a lot of collaborations based on the use cases and the scenarios. So basically, the collaboration is a focus here. So choice of the collaboration will become the necessity in terms of covering the complete system. So that is how collaboration integration is done. So basically, they use for object-oriented systems or object-based systems, and which basically covers the components and interfaces where the collaboration is more. This also has advantages and disadvantages similar to top down and bottom up, where interfaces are not clear, dependencies are more. Likewise, something like a big bang sort of a thing implementation, because most of the components are collaborated together, and only when the collaboration is complete, so integration testing will start. Something like a big bang, we can call it, this collaboration type of testing, but it doesn't require full sort of full-fledged integration testing. Only few tests are enough actually for the end-to-end functionality and the overlap of the collaboration features. So this is a very subjective again to choose what sort of a integration testing we need to have. So we have studied bottom up, top down, big bang. I'll just list out the type of integration testing and the strategies that we have about or seen so far. Top down, bottom up. What is the other one? Big bang. Next one is the hybrid, centralized, layer. But this above five are very important. Most of them are used. Additionally, we can use layer integration, client server, collaboration, integration, etc. So likewise, there are many types, but these are the main type of integration types that can be looked into. Okay. Next. So once we have identified the integration testing types, levels of integration, all the strategies of the integration testing, next step is to identify the environment and the integration models, how we are going to have. So basically, for integration test environment, it's mix of component, unit level, and system testing. It's both. It takes care, right? So definitely we need to have an environment which supports both unit level sort of environment and system level, definitely. So we will have a need of a test driver and stubs. We can reuse the test drivers that were used earlier for component testing. That's why we told that mix of component testing, because for doing the unit level testing, we definitely would have developed some test drivers. Those test drivers can be reused for integration testing. So additional tools like monitors may be required to read and log the data traffic between components and all that. Basically, why we are interested is to interface between these components, and while doing the interface, definitely we need to monitor how the data is getting interacted. So to understand the flow of the data, we need to have uh, test environment identifying different tools such as monitors. Okay. So integration test environment for the software unit and the system integration or software integration test. A test bed is created that is comparable to the test environment for the simulation model. That means we are going to have a test bed. It's basically called as a test bed, which will have an environment which is going to be used for unit level tests as well as the integration test, identifying all the interfaces and the hardware modules and all the necessary inputs, which can be compared with the simulation of the test environment. In the prototype stage, test object is an executable version of a software unit or a set of integrated software units that is developed on basis of the design or generated from the simulation model. So that development could be based on the model or could be based on the code. So we can develop the prototype. Sorry, we can develop the uh, integrated software unit based on the prototypes that have been developed so far for the test environment, and that specific execution or executable version of the software unit will be used by the integrated software units. So that integrated software units are basically developed on the basis of the design or the architecture of the embedded system. That is how the test environment or the test bed is going to be formed for the integration. So the first step is to compile the software for execution. This is basically a build process for the integration test environment. So first step is to compile the software for execution on the host computer. The environment has no instructions, no restrictions on resources or performance, and powerful tools are commercially available. So basically, we need to compile on the host first because we have developed the code in the host, so we need to compile it based on the standards. This makes development and testing a lot easier than in the target environment. We are sure that we cannot afford to have on the scratch from the target only. First host level we will get the confidence by compiling and collecting all the information and installing tool and all that. So this kind of testing is also known as host target testing. First we are going to develop the host based environment and try to test as much at the host, then we will try to target on the target system. The goal of the test on this host compiled software units and integrated software units is to verify their behavior according to the technical design and the validation of the simulation model used in the previous stage. That is incrementally that is going to be validated based on the simulated environment. That is done first, and the second step is software unit or software integration test is to compile the software for execution on the target processor of the embedded system. So we have so far done on the host target based environment. I think we have studied in detail simulator, emulator and all that. It is similar to that same strategy, but here the focus is on the interfaces and the integration of the different modules. So second step is basically we are going to develop for the target, and before actual execution of this software on the target hardware, the compiled version can be executed using an emulator of the target processor. We know that there are emulators, and with the emulator we know we can see the code behavior and the functionality flow and all this at the uh, target system before we execute it. This emulator may run on the development system or on another host computer. So the chances are that the emulator can also be used on different type of portable systems. So goal of these tests is to verify that the software will execute correctly on the target processor. So basically, the software will, if compiled on the host, should work same way as it has been tested on the host on the target system. So that is where it is very important to have this environment identified and used. Okay. So so there is a table here based on the book simulation level for software unit and software integration tests basically. Uh, yeah, this basically identifying based on the test bed that should basically offer the stimulus for doing the tests. So we have embedded software and what sort of a processor and what can be tested on the rest of the embedded system and the plant, what sort of a simulation we have. So software unit, software integration part 2. So first it will be tested on the host as an experimental basis, and the processor we are not going to use the target processor. We are going to use the host processor such as x86 because most of the personal computers will have x86 based architecture, but the tools will support for the compatibility on the target system. So rest of the embedded systems are simulated apart from the experimented host. The second type of is testing the unit or the integration is on the target, the actual environment or the target environment. Here we use the emulator and rest of them can be simulated. So this is how the test environment can be brought up. So but both the situations the test bed must or should give a stimulus for the input of the objects and provide additional features to monitor the behavior of the test object and to record signals basically to validate the signals and all that. They should support this environment and basically this can be done with the help of breakpoints, storing, reading, memory, manipulating the variables, debug steps and call trace, call stack. All this can be using time machines, performance analyzers. All this can be used. They should be supported in the test environment. Okay. So continuation of was integration test environment. In the hardware software integration test, the test object is a hardware part on which the integrated software is loaded. The software is incorporated in the hardware in memory, basically a flash or a ISCO form. The piece of hardware can be an experimental configuration, for instance, a hardware circuit board containing several components including memory. So hardware is the focus here, hardware software integration. The goal of the hardware software integration test is to verify the correct execution of the embedded software on the target processor in cooperation with the surrounding hardware. So that's what is the elaboration of what we have defined hardware software integration. Because the behavior of the hardware is an essential part of this test. It is often referred to as hardware in loop (HIL). So there are different types of in loop situations: software in loop, simulation in loop, hardware in loop. So basically, these are all integration test strategies that are going to be used. So that is where it's necessary to identify the test environment for those hardware where we need to have an integration. Continuation of integration test environment. The test environment for the hardware software integration test will have to interface with the hardware. Depending on the test object and its degree of completeness, the following possibilities exist. Basically, it offers input stimuli with signal generators, output monitoring with the oscilloscope or a logic analyzer combined with the data storage devices, in-circuit test equipment to monitor system behavior on points other than the outputs. So these are some of the environment dependent tools that can be used. Then simulation of the environment of the test object in a real-time simulator. So what we do is basically we have a test hooks or interfaces from the target systems. With the help of those hooks, these tools will be plugged and logic analyzers, oscilloscopes, or signal generators that can act as an input or output to conduct the test. That is what the meaning of the test environment here. Integration test environment. Yeah. So in integration test environment, basically we identify all the stimulated inputs and we'll focus on the captured output and the tools that are used that are going to be used for capturing the output so that the end-to-end path is being verified. So that is the focus of integration test environment basically. So we will continue the test integration and integration environment in the next session, and we'll try to elaborate more on the uh, integration environment and generating test cases from use cases, example of use cases, and how we can generate, and we'll also try to understand regression testing, etc. in the next class.